Today we will see how to convert a left linear grammar to a right linear grammar. So before converting it, we will see what is linear grammar, what is left linear grammar, what is right linear grammar. Then what are the disadvantages of left linear grammar, and how to convert that left linear grammar to the right linear grammar. So linear grammar, as you can see here on the screen, linear grammar is a context-free grammar that has at most one non-terminal symbol on right-hand side of each grammar rule. So whatever production rule you have, so in all that production rules, you should have at least one non-terminal symbol on the left-hand side of the grammar of the production rule. The rule can have only terminals also. On the right hand side of production, you can have only terminals also. So you can see the example here. This is the linear grammar. In the first production rule, you can see this A is a non-terminal. In second production rule, you can see B is a non-terminal. And in third, you can see this B is non-terminal. And rest, this small alphabets A, B, they are terminals. So this is the example of linear grammar. Now this linear grammar, as I said, there are two types, left linear grammar and the right linear grammar. So in case of left linear grammar, the non-terminal is the first symbol on the right hand side of the production. Non-terminal is the first symbol on the right hand side of the production. So if you'll see this example here, we have two production rules. First, S produces AA, and here this A derives AB. So when it is A derives capital AA, so here you could see this capital A, this is your non-terminal, and this is the first symbol on the right hand side of the production. And if this is the case, you will call this as a left linear grammar. In case of right linear grammar, this non-terminal will appear on the, or this non-terminal is the first symbol from the right hand side of the first symbol on the right hand side of the production rule. But this first symbol will be from the right hand side, or in other words, I'll say this non-terminal is the last symbol on the right hand side of the production. So you can see here this non-terminal A, this is the last symbol on the right hand side of the production. It means from right side, this is the first symbol. And in case of left linear grammar, this non-terminal is the first symbol from the left hand side. So this is the difference between left linear grammar and the right linear grammar. Now, left linear grammars, they are a little complicated. So if you have, you could see here, this is the production rule. This is A derives B, A, B, C. And if we want to use this production rule to derive this string A, B, B, A, B, C. So, and the B has these two production rules, C, B or D. So to convert this or to expand this B to get this string, you will need to check, you will need to expand B first. And when you will expand B, either you can expand B to this CB, or you can expand this B to D. For that, whether to choose a correct alternative for the expansion of B. To expand this B, you will need to choose the correct alternative, either CB or D. So again, to choose the correct alternative, you will have to see the production rule of C and production rule of D, so that to guess whether the C will expand eventually to ABB, this is the starting of the input string, or D will get expanded eventually to get this ABB string. So you will have to go down to the various production rules to identify which correct alternative you need to choose to get the desired input stream. And that is a reason it is very complicated, and it is a very recursive process. You have to go on checking next production rules. So that is the reason it is difficult to design the parsers for the left linear grammar, right? Because as I said, if you want to check whether your statement is syntactically correct or not, so you take the help of parse tree. But parse tree, again, it is a it is a pictorial format, and any compiler cannot process it, or it cannot generate that parse tree. So I mean, it can generate the parse tree, but there should be the way. There should be the representation of past in such a way that you can programmatically you should be able to implement it. And for that reason, you have different parsers. So parsers, with the help of parsers, you can the task which your parse tree are doing, the same thing the parsers are doing. So parse trees can be checked or verified or can be generated in the form of parsers. So for left linear grammar, generation of such parsers is very complicated process. So this is one of the disadvantage of left linear grammar. Another thing which you can see here, if you have this A derives A alpha, where alpha is some set of terminals, and this A is again your non-terminal. So I need to in this design mode. So here, if you could see, if you want to expand it, so here you will be having this A, then this A, it will get expanded to A alpha. So this A got expanded to A alpha. Now again this A, again this A, it will again get expanded to A alpha. Now again this A, because this non-terminal A, it appears as a first symbol on the right hand side of the production rule. So definitely you will, it is compulsory for you to expand that non-terminal first. And this process, it continues to for the expansion. And you can see here it generates the skew tree, and it becomes here there is no scope of expansion on the right hand side of each level of the tree, because every time you'll need to expand the left hand side of this tree first. And that is a reason we need to avoid this recursion, we need to remove, or we need to convert this left linear grammar to the right linear grammar. In case of right linear grammar, as you know, the non-terminal, it appears as a last symbol. So you can very easily identify if this is your ABC is the string, you can very easily consider, or you can identify whether this particular production rule can be used to get the desired input string, or you have to try some other production rule. So that is the reason it becomes very easy to guess which production alternative to use, which production rule to use, so that eventually you can expand the non-terminals to get the input string. And that is the reason it is easy to develop the parsers for right linear grammar also. So to convert the left linear grammar to right linear grammar, so there is an algorithm which I asked you to note down in the last lecture. So this is your left linear grammar, this is right linear grammar, this is its equivalent right linear grammar. So when we will say both are equivalent, we will say they both are equivalent when they will accept the same language, right? So this is the algorithm. We will start from here. If you can see the algorithm, as you can see on the screen, the algorithm on the following slides assume that left linear grammar doesn't have any rule with start symbol on the right hand side. And if you have some such rule, then we need to add such type of production rule. So here, if S is your start symbol, and if you want your start symbol on the right hand side, then you should add this some new non-terminal, and that derives your start symbol like that. And basically, when you are adding such type of a production rule in your grammar, so you will say, we call it as that your grammar is augmented. And basically, when you implement the parser, so that time to ensure that you reach to the root of the parse tree, this augmented this particular production rule, it plays very important role. So usually that there is a practice to add such production rule, uh, so that your start symbol will appear on the right hand side. So usually this used to be the very first statement in the grammar. So these are few notations. S start symbol, A and B are non-terminals, P is zero or more number of terminals, and here this particular symbol epsilon, it denotes the empty symbol. So this algorithm you have already noted. So all the four steps, if it is there in front of you, if you have jotted it down in your copy, so I think it will become easy for you to understand which steps are used for the conversion. So this is your left linear grammar, and we need to convert this left linear grammar to right linear grammar. I want you all to take a note of this. So you have here these two production rules you have, right? And if you could see here, rule number 2, here it is mentioned in the left linear grammar. If you have something like this, some production rule like this, A produces, then if you have set of terminals, A derives set of terminals, zero or more number of terminals, then you have to add this such type of production rule in your grammar. So S produces PA. So this set of terminals which are there, that you have to use, and the non-terminal on the left hand side. So this you have to combine, and you have to put it for the start symbol S. So implementing this rule here, this is A derives AB. This is the set of terminals. So obviously, if we'll apply this rule, S produces PA. So here P is small ab, and P is small ab, and A is your non-terminal. So applying this, you will get ABA. So S derives ABA. So that is the reason you have inserted this production rule in its equivalent right linear grammar. Then if you have this statement, something like this, of this form, S derives AA, where S and A are non-terminals, then you should convert this statement or this production rule to A derives P. So here you will get A derives P. So applying this to, you got the equivalent non-linear equivalent right linear grammar. And if you observe both of them, they are accepting the same set of language, and that is the reason they are equivalent. This is a left linear grammar. You have to convert this left linear grammar to its equivalent right linear grammar, and here you have to make a new start symbol, and that is the reason this uh, statement is added here, or this production rule is added here. Now you have to convert this left linear grammar uh, to the right linear grammar. So I'll give you 10 minutes time, and you finish it off, and at the end we will check the result.